Imagine you've been given basically the ultimate power to build an entire universe from scratch.
Wow, okay. That's a big responsibility.
Right, like you have to decide exactly how everything works from the very ground up. You need rules for how things are categorized. You need a contingency plan for when disasters inevitably strike.
Because they definitely will.
Oh, absolutely.
Yeah.
And, you need a way for your isolated little universe to actually communicate with the outside world. It sounds like the premise of some epic science fiction novel.
Yeah, it really does.
But what we're actually talking about today is the day-to-day reality of writing computer software. Welcome to the deep dive. I'm so glad you're joining us today.
It's great to be here.
So our mission today for you, the listener, is we are going to take a seemingly dry, highly technical subject. Specifically, we're looking at Lecture 7 from the MIT 6.092 Java course. This is from way back in January 2010.
A real classic in the computer science world.
Yeah, exactly.
Yeah.
And we're going to extract the really powerful universal logic that's hidden within all that code. Okay, let's unpack this.
Sounds good. Let's do it.
We're looking at three main pillars today. How programmers organize concepts, which they call inheritance, how they handle disasters, known as exceptions, and how they talk to the outside world, which is I/O.
Yeah, and while the source material is explicitly about Java programming, the underlying concepts actually mirror how we humans categorize the physical world.
Really, like philosophically.
Completely. It's about how we set boundaries and manage the unexpected. We're looking at the pure philosophy of structure, but just, translated into digital commands.
I love that. So let's dive into that first pillar. How programmers avoid doing the same work twice and create rules for their digital worlds. This brings us to what the source calls the dude ecosystem.
Right, the dude ecosystem. It's a great example.
But before we get to the dude, we have to talk about interfaces. In the lecture, an interface is basically presented as a contract, like an unyielding legal document.
Exactly. Think of an interface as a universal guarantee. If a class, which is just a blueprint for a digital object, signs this contract, it is legally obligated by the system to fulfill it.
Okay, so give me an example from the lecture.
So the MIT material uses an interface called icar. It has a strict rule. If you sign the icar contract, you must implement a specific method called getNumWheels.
Like you have to be able to tell the system how many wheels you have.
Right. So if you write a big rig class and you agree to the icar contract, that big rig must return the number 18 when asked.
And if it doesn't?
The program just refuses to run. It's that strict.
Wow. And they also mentioned a homework assignment in the source involving sprites.
Yes, sprites in video games.
Right, so like say you have a sprite interface and you have shapes like an oval.
Exactly. Or you have a controller called a straight mover.
And because of that interface contract, the developer can draw or move literally anything on the screen as long as it follows the contract. The system doesn't need to know what the object actually is, just that it signed the sprite contract.
Precisely. It allows developers to build systems that trust the objects they are interacting with without micromanaging them.
Okay, that makes sense. But this brings us to my favorite part of the MIT lecture, the dude class.
It's such a perfectly geeky example.
It really is. So the professor sets up this core example. You have a class called dude, and this dude has some basic stats. He has a name, he has 100 health points, or HPS, 0 magic points EMP.
Because he's just a regular dude, no magic.
Exactly, just a guy. And he has one specific action he can take, a method called punch face.
Which takes another dude as a target.
Right, punch face, dude target. And if he does that, it deducts 10 HP from the target. Pretty straightforward.
Yeah.
But then the lecture asks, what if you want to make a wizard?
And here is where the instinct for a beginner is to just copy all that code from the dude and paste it into a new file for the wizard.
Which the lecture absolutely screams at you not to do.
Yeah.
It literally says, don't act now, you don't have to copy and paste. By inheritance.
It's a great pitch.
So instead of copy, you just type wizard extends dude, and that's it.
That's the magic of it. By extending dude, the wizard gets everything the dude has. Well, except for completely private lockdown fields or methods, but basically everything else.
So the wizard gets the 100 health points.
Yep.
And the name.
Exactly. And crucially, a regular dude can punch the wizard using the exact same code.
Like dude1.punchface, wizard1.
Right, because as far as the program is concerned, a wizard is just a specialized type of dude. The wizard can be punched, and it can punch back.
But the wizard isn't just a dude. It's better.
Well, it has more features. The wizard gets its own new abilities on top of the inherited ones.
Huh.
The lecture shows how you can give the wizard an array list of spells.
Oh, like an expandable inventory of magic.
Exactly. And those spells actually cost the ball to use, which the wizard now has, unlike the regular dude.
Okay, so let me ask an active question here, just to clarify. So when I make let's say a Grand Wizard class.
Okay, a grand wizard that extends wizard.
Right. And my Grand Wizard tries to punch someone.
Hmm.
But I didn't write any specific punching code in the Grand Wizard file. Does Java just, like, look up the family tree?
That is exactly what it does. It runs an ancestry search.
Oh, wow.
Yeah, Java checks the grand wizard file, no punch code. Then it checks the parent, the wizard file, still no punch code.
Because we didn't put it there either.
Right. Then it goes up one more level to the dude, and boom, it finds punch face and uses it.
That is so incredibly efficient.
It is, and it lets you do some really cool tricks. You can actually put disguises on your objects using a concept called casting.
Wait, casting like spells.
No, casting like pouring metal into a mold. You can tell Java to temporarily treat your grand wizard strictly like a basic dude.
Oh, I see in the notes here, you just write it in parentheses, like, do Grand Wizard 1, and then you can call a dude method, like,
Look,
say name.
Exactly. It forces the system to ignore all the fancy magic stuff for a second and just deal with the foundational dude layer.
Okay, I have to push back here, though. If inheritance is so great, and it saves all this time, why not just inherit from everything?
What do you mean?
Like, give me a character that inherits from a thief and ED elf. I want all the stats. Why limit it?
What's fascinating here is that the creators of Java foresaw that exact temptation, and they strictly outlawed it. You can only have one parent class.
But why? It seems like a limitation.
It prevents what the lecture calls the bad elf problem.
The bad elf problem. That sounds hilarious.
It does, but it's a serious logical nightmare for a computer. Imagine you try to make a bad elf that inherits from both thief and elf.
Okay.
And let's say both thief and elf have a method called sneak up.
Oh, I see where this is going.
Right, but they implement it differently. The thief sneaks up by hiding in shadows. The elf sneaks up using an aura of silence. If you tell your bad elf to sneak up, what happens?
The computer panics. It doesn't know which set of instructions to use.
Exactly. It creates an unresolvable ambiguity. And computers despise ambiguity. So single inheritance keeps the hierarchy stable. You only ever have one direct parent to look up to.
Okay, that makes perfect sense. So we just established this beautifully structured world, dudes, wizards, a clear family tree. But what happens when the wizard tries to cast a spell that doesn't exist?
Or when the perfect code hits a wall.
Right, right. That brings us to our second pillar. Handling the unexpected, or as programmers call it, exceptions.
Exceptions are essentially the contingency plans of the digital world.
So an exception is just when something unexpected happens, right?
Pretty much. And lecture gives some really common examples, like trying to use a method on a variable that's completely empty.
Oh, the dreaded null pointer exception.
You know it well. Or say you have an array list that only holds 5 items.
And you try to grab the 6th item.
Exactly. That triggers an array indexed out of bounds exception.
That is a mouthful.
Yeah.
And there's also the runtime exception, which the source mentions is like trying to shove text into a number variable.
Right. Trying to do math with the word apple. The system just throws its hands up.
And when you say throws, that's actually the literal terminology they use, right?
It is. When Java gets confused or hits an impossible instruction, it creates an exception object. You can think of it as a little package of useful information about what just went wrong.
And then it hurls it.
Yeah.
It's like a worker finding a broken machine on an assembly line and just throwing a giant red flag into the air.
That's a great analogy.
Someone better catch it, or the whole factory is shutting down.
Exactly. And the syntax reflects this perfectly. There are 2 different words to know. First, there's throws with an "s" at the end.
Okay, what does that do?
That acts as a warning label on a method. It tells other programmers, hey, if you use this method, it might throw an error.
Like a hazardous material sign?
Precisely. And then there's throw without the "s." That is the actual action of hurling the error object when things actually break.
So if a red flag gets thrown, how do you catch it?
Java demands you build a safety net. You have to wrap the dangerous code in what's called a try-catch block.
Try-catch.
Right. You say, try this block of code, and right after it, you have a catch block that specifies exactly what to do if a specific error is thrown. It handles it gracefully instead of crashing.
Or you just rethrow it.
Yes, you can pass the responsibility to someone else.
Here's where it gets really interesting. The lecture describes this as an intense game of hot potato.
It is entirely a game of hot potato.
So let's say we have a method called get, and it fails. It throws a red flag to the method that called it, which the lecture calls do bad.
And if do bad doesn't want to deal with it, it doesn't have a try-catch block. It just throws it further up the chain.
Main, the very top of the program.
Right.
But I have to ask, what if main, the absolute big boss of the program, just dodges it too? What if literally N01 catches the red flag?
Then you have a total crash.
The whole thing just died.
The whole thing dies, Java gives up entirely. But before it dies, it prints out something called a stack trace.
The stack trace.
Yeah, it's essentially a detailed paper trail. It prints out exactly who passed the buck and where the code died.
Like a post-mortem report.
Exactly. It'll say something like, error at your class.get, called by your class.doBad, called by your class.main. It traces the exact path of the failure. It is the ultimate debugging tool for a programmer.
So you can literally track down exactly which manager dropped the ball.
You can find the exact line of code where it all started.
That is fascinating. Okay, so now our code is organized beautifully with inheritance, and it's safe from totally crashing because we have exceptions and safety nets.
We have a very stable universe.
Right, but it's completely isolated.
Mm.
Right now, our little digital universe is just sitting alone in a dark room. How does it actually take in new information from you, the user, or from, like, a hard drive?
That brings us to our final pillar, I/O, or input and output streams.
Output seems pretty easy. We all know system.out.println from day one of learning Java. You just tell it to print words, and it prints them.
Output is relatively straightforward. Input, however, requires a weirdly specific setup.
Weirdly specific is putting it mildly. When I was looking at the source, it looked like Russian nesting dolls of data.
That is the perfect way to describe it.
The lecture outlines 3 distinct layers you have to build just to read a single piece of text. Let's walk through them. Layer 1 is the input stream.
Right. The input stream is just a raw stream of numbers, ones and zeros, like 100, 10, 1010, just flowing endlessly from a hard drive or a network cable.
It's completely illegible.
Exactly. The program can't understand it as human text yet.
So you take that raw stream and you wrap it in the second doll, the input stream reader.
The translator. It takes those raw bytes and converts them into actual characters. So now, instead of ones and zeros, you get an O, then a K, then an A, then a Y.
But it's just a trickle of single letters.
Right, which is really inefficient if you want to read a whole paragraph.
So you need the third biggest doll, the buffered reader.
The buffered reader is like a waiting room. It groups those single characters line by line, so instead of individual letters, it hands the program a full, coherent sentence, like, okay, awesome, cool.
So if you want to apply this to reading a simple text file, you use a file reader, wrap it inside a buffered reader, and then what?
Then you just use a while loop. You tell the program to keep reading line by line over and over until it hits null.
Until there's nothing left.
Exactly.
Okay, I have to complain on behalf of the listener here.
Go for it.
This seems ridiculously overcomplicated. Why on earth do I need 3 different objects just to read a simple text file? Why not just have one single command that says read file?
It does seem like overkill at first glance, but if we connect this to the bigger picture, the genius here is modularity.
Modularity, like interchangeable parts.
Exactly. Because these streams are separated into distinct layers, you gain incredible flexibility. Let's say you write a program that reads data from a local text file using a file reader, but then, a month later, you decide you want your program to read data streaming live from a network connection instead.
Oh, I don't have to rewrite the whole thing.
Right. You don't have to touch the buffered reader logic at all. The waiting room still works exactly the same. You just swap out the local file reader for a network stream. It beautifully separates where the data comes from how it's actually processed.
Wow. Okay, that actually is pretty genius. It's future-proofing your universe.
Exactly.
Okay, let's zoom out and summarize this amazing journey. We have learned how developers build logical family trees with inheritance. We learned how to safely catch the chaos of crashing code with exceptions. And we learned how to pipe in data from the messy real world using layered modular I/O streams.
It's the complete toolkit for building a digital reality.
And the MIT lecture actually forces the students to pull all of this together in their final homework assignment.
The magic squares assignment.
Right. They have to evaluate magic squares. They have to read 2 separate text files full of numbers, which requires those I/O streams we just talked about.
And handle the exceptions if the files are missing or broken.
Exactly. And then they have to check if all the rows and columns in the grids perfectly sum to the number 15.
Yeah.
It really ties everything together beautifully.
It's a great practical application, but, this raises an important question.
Oh, I like where this is going.
We just spent this whole deep dive looking at how programmers use strict contracts, single-parent inheritance, and rigid error handling to build software. We demand that the computer's universe be perfectly categorized.
Yeah, no bad elves allowed.
Right, no bad elves. But if software is increasingly running our daily lives, approving our loans, filtering our job applications, routing our traffic, aren't we forcing the incredibly messy, multi-layered reality of human existence into a digital bureaucracy that can only ever have one parent class?
Oh, wow.
Next time a computer system says error or won't let you submit a form because your life doesn't fit its exact parameters, ask yourself, is the data actually wrong? Or is the rigid inheritance tree just failing to capture the complexity of the real world?
That's going to keep me up at night. Seriously, next time I get a generic error message, I'm going to wonder if I'm just an unhandled exception that the system wants to pass off to a manager.
We're all just trying not to cause a stack trace, really.
Truer words have never been spoken. Well, thank you so much for breaking all this down with me, and thank you, the listener, for joining us on this deep dive into the architecture of code. Keep questioning the rules of your universe. We'll catch you next time.